Hello, this is our project on disk collision. We are John Losee.
And Victoria Palacios. For our problem, we were to demonstrate the proper collision of two circles while allowing the user to control the velocities of each circle. The solution we broke into three parts. First, you need to detect the collision, then compute the new velocity after the impact of the collision, and then you animate the projections.
And this is our video. So, so here we're just demonstrating the different manipulating abilities. We can scale the size of the radii. We can translate the disks, and um, we can also change the direction of the vectors and the length of the vectors. Right now, the animation is currently on, and as you can see, the velocities are changing after impact based on our mathematical computations. And so here's just some more variations, different vector lengths, directions, and here we are again, starting again with different sizes for the radii, just to demonstrate different versions. And as you can see, the smaller, whichever disk is smaller, moves more quickly. So, as I said, we can scale the radii by dragging the mouse after choosing the green circle that was on the edge of each disk. We can also translate the vectors. We can make them shorter or longer, and we can change their direction. And we can also translate the disks themselves. So to detect collision, we start by utilizing the quadratic formula to compute the time at which the two disks will collide. And so what goes into the quadratic formula are the dot product of the vector between v2 and v1. Another part is the dot product between the vector of the two centers, and again with v2 minus v1, we multiply that by 2. And then the other part is from the dot product of the vector between the centers minus the sum of the radii. And then our code gives us the time at which the disks collide, and if they don't collide, it returns positive 2. But if they do collide, then it uses that time to show the prediction. And then on our program, we actually draw new disks to show where they will collide with each other. And then when the user presses the animate button, the disks are actually drawn, traveling along the vectors that they started with. they collide and then they bounce off at the new vectors. And this only happens when the distance between the centers of the predictions is equal to the sum of the radii.
Okay. Well, once the time of contact has occurred, we use two values, the vector center 2, center 1, and its normal to derive the value for a vector I will call delta. Then after we derive delta, we use a ratio of masses to compute the fraction of the delta what the fraction of the delta will be added to the original velocities to find the post-collision or new velocities. Now the delta is a vector in the normal direction with its magnitude related to the normal components of the initial velocities. We take the dot product of the vector that goes from the center point of disk 1 to the other center of disk 2 at the point of collision and its normal times the normal to compute delta. Now, to compute the ratio of masses, we must consider each disk separately because the new velocities are two separate entities. So for each disk, you would take the mass of the other disk divided by the average of the masses of the two disks. Finally, to find the new velocity of each disk, you multiply the delta vector by the ratio of masses scalar and add the product to the original vector. Some issues we had with our code was the initial point of collision was also detecting the intersection of the disk, which was incorrect. The velocities were updating erratically because in our new velocity function, we were manipulating messing with the original velocities as well, and the animation was jumping or incomplete because we were using the wrong functions to translate the disks. Our sources were our lecture notes from class and one of the notes that were provided to us by in the Dropbox for the course.